On December 16, 1944, at 0531 hours, near Moncha, on the German-Belgian frontier, Colonel Oscar Alfred Axelson of the United States 46th Artillery Group found himself scrutinizing classified ammunition containers in the dim pre-dawn light. He understood that his impending choice would contravene directives issued from the highest echelons of Allied command. Through his field glasses, he observed German formations converging, preparing for what would unfold as Hitler's final, desperate push into the Western Front. This offensive was codenamed Operation Watch on the Rhine. The 38th Cavalry Squadron, tasked with defending the northern flank of what history would later recognize as the Battle of the Bulge, was on the verge of being overrun. "Sir, German artillery preparation has commenced," his operations officer reported. "The 38th is requesting immediate fire support." Axelson turned his gaze towards the towering stacks of shells, each bearing the classified designation of T-98 proximity-fused rounds. These munitions had been strictly prohibited for land use since their inception due to their unparalleled secrecy. Indeed, even a majority of American commanders were unaware of their existence. The underlying technology involved miniaturized radio transmitters. Upon reaching precisely 30 feet above the ground, these rounds would detonate, unleashing a lethal cone of fragments that rendered conventional foxholes entirely ineffective as protection. "Load the VT shells," Axelson commanded, employing the code name, a reference to variable time, intended to mislead enemy intelligence. "We're going to need every asset at our disposal." Within 47 minutes, Axelson's unauthorized directive would introduce German ground forces to a weapon that would fundamentally alter the concluding months of the Second World War. The shells, programmed to detonate above German positions, incorporated technology so advanced that German scientists had deemed it beyond possibility. Each round was a testament to an industrial capability that starkly highlighted the disparity between American manufacturing prowess and German assumptions about their adversary. The very calculus of warfare was about to be rewritten. Every shell was designed to detonate at an approximate altitude of 30 feet, dispersing supersonic steel fragments that traveled at 3,000 feet per second, saturating a 60-yard radius with lethal force. No depth of excavation, no configuration of a foxhole, and no thickness of overhead cover constructible under combat conditions would offer any sanctuary against this metallic downpour from the sky. The proximity fuse, according to official United States military assessments, represented the third most significant technological advancement of World War II, surpassed only by radar and the atomic bomb. Yet, unlike those other breakthroughs, its very existence remained a mystery to German forces until they were perishing beneath its devastating effects. The device, while elegant in its fundamental concept, presented an immense challenge in its execution. It housed a miniature radio transmitter and receiver, compact enough to reside within the nose of an artillery shell. This tiny apparatus was engineered to withstand acceleration forces 20,000 times that of gravity, and sufficiently sophisticated to ascertain its precise distance from the ground, triggering detonation at the optimal height for maximum lethality. Each fuse contained 4 vacuum tubes, not 5 as sometimes erroneously reported, functioning as a self-contained radio station compressed into a space smaller than a coffee cup, and fortified to endure stresses that would liquefy human tissue. Development commenced in 1940, consuming $1 billion in 1940's currency, equivalent to approximately $15 billion in today's valuation. By the latter half of 1943, American factories were manufacturing 40,000 proximity fuses daily, a rate that would eventually climb to 70,000 per day by the war's conclusion. The British scientific delegation that first encountered this technology described it as the war's most exceptional scientific accomplishment. The production figures unequivocally demonstrated American industrial dominance. A total of 22,073,481 proximity fuses were manufactured between 1942 and 1945, with 21,685,000 157 dispatched for combat deployment and 388,324 allocated for testing. Each fuse comprised roughly 130 components, fabricated to tolerances of 1/10,000th of an inch. Assembly was conducted in sterile environments by 110,000 workers, many of whom were unaware of the ultimate purpose of their intricate labors. The challenge of power supply was ingeniously resolved through a wind-driven generator, activated only after the shell's departure from the gun barrel. A small propeller, shielded during acceleration, would extend into the airstream, generating electricity to charge capacitors that powered the radio circuit operating within the 180 to 220 MHz frequency range. This design ensured the fuse remained entirely inert until fired, posing no handling risks, undetectable by jamming until the final moments of its trajectory. The inaugural large-scale deployment of proximity-fused shells against ground targets occurred at 0618 hours on December 16, 1944, precisely 47 minutes after the commencement of the German offensive. Colonel Axelson's 46th Artillery Group unleashed their barrage without official sanction, responding to an immediate tactical emergency. General Eisenhower would not formally seek authorization until December 19th, with all restrictions subsequently lifted on December 21st. The impact was swift and devastating. German soldiers advancing through the pre-dawn gloom instinctively sought refuge in their prepared foxholes as American artillery commenced. This was standard procedure, a tactic they had employed countless times. However, instead of impacting the earth, the shells detonated in the air above them. The fragments descended at angles that rendered foxholes utterly useless. The 99th Infantry Division's after-action report documented the profound effect. Concentrated VT-fused artillery fire on German assembly points near Krinkel resulted in extraordinary casualties among the leading battalions within 12 minutes of the fire mission's initiation. Enemy medical services were overwhelmed. Advancing formations were compelled to tread over their fallen comrades to continue their assault. By December 23rd, military intelligence estimated that 2,000 German soldiers had perished from proximity-fused rounds during the engagements around Malmö, where artillery battalions had inflicted heavy losses upon SS units. Some attackers, reportedly so unnerved, charged directly into artillery fire, shouting, "Kamerad!" The psychological toll far surpassed the physical devastation. To comprehend why proximity fuses rendered traditional defensive positions obsolete, one must grasp the physics of aerial burst destruction. A standard high-explosive shell detonating on ground contact propels 50% of its fragments into the earth, 45% horizontally, and a mere 5% upwards. A soldier in a properly constructed foxhole possessed a 90% chance of survival against conventional artillery. The proximity fuse catastrophically altered these odds. Detonating at 30 feet altitude, 100% of the fragments traveled downwards or outwards in an inverted cone pattern. The lethal radius expanded from 25 yards for ground bursts to 60 yards for air bursts. More critically, the fragments impacted at a 30 to 45-degree angle, perfectly aligned to penetrate foxholes, trenches, and rifle pits. The area rendered lethal by fragments increased from 60 square feet with conventional fuses to 3,000 square feet, a 50-fold improvement that rendered traditional field fortifications largely ineffective. This was not merely an incremental enhancement in artillery effectiveness, it represented a fundamental paradigm shift in how artillery could be employed against infantry. The shells themselves stood as monuments to American precision manufacturing. The miniaturized components were engineered to function after enduring forces that would obliterate conventional electronics. The 4 vacuum tubes, a triode for oscillator detector functions, a pentode for amplification, a thyrotron as the trigger switch, and occasionally a diode for rectification, were specially hardened variants bearing no resemblance to their commercially available counterparts. The development of the proximity fuse epitomized the pinnacle of American scientific and industrial collaboration. In August 1940, the British Tizard mission shared their military secrets with America. including early radar research and the theoretical groundwork for a proximity fuse. While British scientists had validated the concept, they lacked the industrial capacity for its development and mass production. The National Defense Research Committee, established in June 1940, designated the Proximity Fuse project its second highest priority, following radar. The Johns Hopkins Applied Physics Laboratory became the central hub for development, while American industry geared up for production. The challenges were monumental. The fuse had to withstand 20,000 Gs of acceleration, operate across a temperature range of -50 to +120 degrees Fahrenheit, spin at up to 30,000 revolutions per minute, and function reliably after months of storage in diverse conditions, from humid Pacific islands to frozen European depots. Project Section T, the code name for the Proximity Fuse Initiative, engaged 3,000 scientists and engineers at its zenith. They pioneered new plastics impervious to shattering under acceleration, developed miniature vacuum tubes capable of withstanding forces that would destroy conventional electronics, and devised assembly techniques achieving accuracies measured in 10,000ths of an inch. The first successful test occurred on January 29, 1942, when a proximity-fused shell obliterated a drone aircraft over Chesapeake Bay. By August 1942, the USS Cleveland was equipped with proximity-fused anti-aircraft shells, yielding spectacular results. Japanese aircraft attrition rates increased dramatically. The USS Helena etched its name in history on January 5, 1943, downing a Japanese dive bomber off Guadalcanal using only 4 proximity-fused shells. However, the technology was deemed too sensitive for land deployment, where the risk of enemy recovery of unexploded ordnance was significant. This restriction persisted until the German offensive in the Ardennes threatened to cleave Allied forces, compelling field commanders like Colonel Axelson to make unauthorized decisions that ultimately proved sound. Prior to their deployment against ground targets, proximity fuses had already demonstrated their revolutionary efficacy in naval warfare. Operating at sea eliminated the peril of enemy capture, permitting unrestricted engagement against Japanese aircraft. The statistics were compelling. Ships utilizing proximity fuses required an average of 310 rounds per aircraft kill, compared to 1,162 rounds for conventional ammunition. By 1944, proximity-fused shells accounted for 25% of all ammunition expended, yet were responsible for 51% of aircraft destroyed. During the Battle of the Philippine Sea in June 1944, proximity fuses contributed to what became known as the Great Marianas Turkey Shoot. With Japanese aircraft losses exceeding 400 planes, the technology that would decimate German infantry had been perfected against Japanese aviators. The British had commenced employing proximity fuses against V-1 flying bombs. On June 12, 1944, mere days after D-Day, anti-aircraft batteries positioned along the English coast witnessed their kill rate escalate from 17% to 79% within 4 weeks. General Sir Frederick Pyle, commander of Anti-Aircraft Command, lauded it as the most remarkable scientific achievement in the annals of warfare. These triumphs made the restriction on ground use increasingly untenable. Field commanders were aware of the technology's existence and grew increasingly frustrated as their infantry sustained casualties that could have been averted by proximity fuses. The crisis of the Battle of the Bulge finally shattered this bureaucratic inertia. German intelligence had, in fact, received intelligence regarding proximity fuses. In October 1944, General Field Marshal Albert Kesselring's staff observed a marked increase in Luftwaffe losses attributed to Allied anti-aircraft fire. They recovered metallic fragments exhibiting unusual scoring patterns, indicative of aerial detonation. Kesselring's report to OKW, Oberkommando der Wehrmacht, stated, "Evidence suggests the Americans possess altitude-triggered ammunition. If adapted for ground artillery, the impact on infantry would be catastrophic. Immediate investigation into countermeasures is recommended." The response from Berlin, unearthed in captured archives, dismissed his concerns. Technical evaluation concludes proximity detonation under battlefield conditions is impossible. American anti-aircraft improvements are attributed to radar direction and increased gun density, no action required. This dismissal would prove exceedingly costly for the Wehrmacht. German scientists had actually begun efforts to develop proximity fuses as early as the 1930s, creating 30 to 50 distinct designs, including acoustic fuses triggered by engine noise, electrostatic field devices, and radio wave systems. None achieved operational status. Hitler's 1940 directive, which mandated the termination of any development projected to take longer than 6 months to reach production, effectively stifled their program. The irony was profound. During the Battle of the Bulge, German forces captured approximately 20,000 proximity fuses, but failed to recognize their significance. German engineers had concluded that such technology was infeasible due to the immense acceleration forces experienced during firing. They literally held the most crucial intelligence coup of the war in their hands, utterly oblivious to its value. 5 American corporations were responsible for the final assembly of proximity fuses. Crosley Corporation, producing 5.2 million units. Sylvania, with 5.7 million. RCA, at 2 plants, a combined 5.9 million. Eastman Kodak, 2.4 million. And McQuay Norris, 2.9 million. Sylvania's plant in Ipswich, Massachusetts, stood as the single highest producing facility, accounting for 26% of the total output. The Crosley Corporation's plant in Cincinnati employed 8,000 workers, manufacturing up to 16,500 proximity fuses daily at its peak production rate. Their quality control systems detected defects as minute as 15,000ths of an inch. The plant consumed more electricity daily than entire German cities. Air conditioning systems maintained temperatures within a 2-degree tolerance to prevent thermal expansion from affecting precision measurements. Quality control rejected 28% of completed units that failed to meet specifications. This rejection rate, which would have been considered catastrophic for German production, was deemed acceptable by American planners due to the sheer volume of production. They could afford to discard more precision components daily than Germany produced in an entire month. Sylvania dominated component manufacturing, producing 95% of the miniature vacuum tubes, over 100 million in total, and employing 10,000 workers across 15 plants dedicated exclusively to the VT program. Over 100 American companies participated across the supply chain, with more than 2,000 suppliers, ranging from raw material processors to intricate machine shops. The workforce was predominantly female. At Sylvania's Ipswich plant, 9,000 out of 10,000 employees were women, many recruited from surrounding communities. They worked in sterile environments with filtered air, utilizing microscopes to verify component placement within tolerances of 0.002 of an inch. Each worker typically performed a single, highly specialized task, repeated thousands of times per shift. By Christmas Day, 1944, proximity fuses were being deployed across the entire Ardennes front. The U.S. Army expended 200,000 proximity-fused shells during the Battle of the Bulge. General Patton, initially hesitant regarding the new technology, became a staunch advocate after witnessing its effectiveness firsthand. On December 25th and 26th, Patton's Third Army reported the confirmed elimination of approximately 700 Germans at Ectan using proximity-fused artillery. His now famous assessment was, "The funny fuse won the Battle of the Bulge for us." This sentiment came from a commander who had previously favored tanks and mobile warfare over artillery. The psychological impact on German forces was meticulously documented through prisoner interrogations. Captured soldiers repeatedly conveyed feelings of helplessness against artillery that detonated overhead. Standard defensive training emphasized seeking concealment in depressions, foxholes, or trenches. Proximity fuses transformed these protective positions into deadly traps rather than safe havens. One captured German officer informed interrogators, Your shells explode precisely at treetop height, always the same height. We tried everything. Deeper dugouts, concrete overhead cover, dispersal tactics. Nothing availed. The consistency of the 30-foot detonation height, achieved through precise radio measurement, created a predictability that was paradoxically more terrifying than random impacts. The Battle of the Hurtgen Forest, which had raged since September 1944, underwent a dramatic transformation when proximity fuses were authorized for use on December 18th. The dense forest, which had provided German defenders with concealment and overhead cover, became a force multiplier for the proximity fuse's effectiveness. Tree bursts had always been lethal, but achieving them deliberately with time-fused shells proved difficult. Proximity fuses detonated consistently at the optimal altitude, whether over open terrain or beneath the forest canopy. The combination of steel fragments and flying wood splinters created a deadly maelstrom against which no field fortification could offer resistance. The 4th Infantry Division's artillery unleashed 12,000 proximity-fused rounds in the first 48 hours following authorization. The division's after-action report indicated a substantial increase in enemy casualties and a corresponding decline in German defensive efficacy. Medical stations reported wound patterns previously unobserved, deep puncture wounds originating from above, concentrated on the shoulders and heads. This engagement served as a grim laboratory for understanding the effects of the proximity fuse. Artillery observers noted a cessation of foxhole use by German soldiers, who instead sought overhead protection within bunkers and buildings. This drove them into concentrated positions, which then became prime targets for conventional high-explosive shells, creating a tactical quandary with no simple resolution. Operation Grenade, the Allied offensive aimed at reaching the Rhine, commenced on February the 23rd, 1945. The Ninth Army expended hundreds of thousands of proximity-fused shells within the first week. German defensive positions, meticulously prepared over months, proved alarmingly vulnerable to aerial burst attacks. The Wehrmacht issued increasingly desperate directives in an attempt to counter the proximity fuses. A directive dated February 10th mandated that all units construct foxholes with a minimum depth of 2.5 meters, incorporating overhead cover constructed from logs at least 30 centimeters in diameter, further protected by 50 centimeters of earth. A revision on February 18th stipulated that movement in areas under artillery threat was permissible only via covered trenches. All positions were required to possess concrete or steel overhead protection. These measures were, in practice, unattainable under combat conditions. The necessary materials and the time required for such extensive construction simply did not exist. A directive dated February 26th tersely stated, "Units will disperse to the maximum distance permitted by combat effectiveness. No more than 2 men will occupy any single position." The capture of the Ludendorff Bridge at Remagen on March 7, 1945, exemplified both the formidable power and the inherent limitations of proximity fuses. When Lieutenant Karl Timmen requested artillery support utilizing VT fuses to impede German retreat across the bridge, the artillery commander denied the request, citing reports that U.S. troops were positioned too close to the target. This documented refusal, found within official U.S. Army historical records, underscored the necessity for meticulous tactical planning when employing proximity fuses to preclude friendly fire incidents. German attempts to develop their own proximity fuse technology starkly illustrated the fundamental industrial disparity between the belligerents. Rheinmetall resumed research in 1944 and successfully tested several hundred working prototypes before the war's conclusion. However, prototypes are distinct from production-ready models. German engineers calculated that the nation would need to construct 15 new electronics manufacturing facilities, train 50,000 specialized technicians, and develop manufacturing processes that did not yet exist within Germany. Their projections indicated a requirement for 500 tons of refined copper monthly, 50 tons of silver for electrical contacts, 2 million precision vacuum tubes, and 100,000 skilled laborers merely to approximate American production rates. Even assuming the availability of necessary materials, German industry lacked the requisite precision machine tools. American factories utilized Swiss-made micrometer tools accurate to 1/10,000th of an inch. Germany's finest machine tools, worn from 5 years of continuous operation, could achieve accuracy of 1/1000th of an inch on favorable occasions. The stringent quality control requirements alone exceeded Germany's manufacturing capabilities. The deeper irony lay in the fact that German scientists possessed a complete theoretical understanding of the technology. Indeed, they had initiated proximity fuse research prior to the Americans. Yet, comprehending theory and achieving mass production were entirely disparate challenges. America had not only engineered a superior technology, but had also established an industrial ecosystem capable of producing it in quantities numbering in the millions. While proximity fuses fundamentally altered ground warfare in Europe, their original application, anti-aircraft defense, reached its apex of effectiveness in the Pacific theater. By 1945, projectile fuses designed to detonate in proximity to a target annihilated Japanese aircraft with a remarkably high degree of success. The looming threat of Japanese suicide attacks, which could have inflicted devastating losses during an invasion of the Japanese homeland, was significantly mitigated by these proximity fuses, also known as VT, variable time fuses. Naval vessels employing these proximity fuses during the Okinawa campaign managed to shoot down 91 Japanese aircraft for every 100 that attacked, a stark contrast to the 25 planes downed per 100 before their introduction. Admiral Willis Lee stated that the proximity fuses were instrumental in saving 100,000 American lives in the Pacific theater. Each enemy plane destroyed by a VT fuse represented one less aircraft that could have impacted American ships. This dual capability, proving devastating against ground forces in Europe and decisive against aerial threats in the Pacific, epitomized the American industrial philosophy: create excellence through mass production and deploy it universally. While Germany struggled to manufacture basic ordnance, it faced an adversary that incorporated advanced electronics into seemingly disposable munitions. Military researchers investigating the effectiveness of proximity fuses discovered they were between 3 and 10 times more lethal than standard artillery against terrestrial objectives. Against the V-1 flying bombs, the success rate of their destruction escalated from 24% to 79%. In naval anti-aircraft operations, the average number of rounds required to achieve a single kill plummeted from over 1,000 to approximately 300. The 50-fold expansion in the area affected by lethal fragmentation fundamentally reshaped the deployment of artillery. Conventional artillery necessitated concentrated barrages to achieve broad area coverage. Proximity fuses, however, enabled dispersed firing patterns to yield comparable results with fewer projectiles. This advancement improved logistical efficiency, reduced wear on gun barrels, and allowed artillery to provide support to more units simultaneously. General Patton reported that proximity fuses empowered his artillery to support advancing ground forces with enhanced effectiveness. Rather than undertaking prolonged preparatory bombardments, artillery could deliver brief, intensely lethal barrages, enabling infantry to advance before enemy forces could regroup. This acceleration of operational tempo contributed to the swift Allied advances witnessed in 1945. However, casualty figures necessitate careful scrutiny. Although various estimates circulated during and after the conflict, no documented evidence substantiates claims of specific, exceptionally high numbers, such as 250,000 German fatalities directly attributed to proximity fuses. What is demonstrably proven is their multiplicative effect on artillery's lethality and their significant psychological impact on German troops. German comprehension of proximity fuse technology evolved slowly and incompletely. Interrogations of prisoners revealed that the majority of German soldiers never understood the nature of the weapon that was targeting them. They spoke of projectiles detonating amongst trees or of aerial mines, failing to grasp the systematic sophistication of the technology. German technical intelligence eventually recognized the advanced engineering involved. Captured German reports dating from March 1945 acknowledged that the American proximity fuse represented a 5-year leap forward in the miniaturization of electronics. Replicating it would necessitate a complete overhaul of the electronics industry, the sourcing of new materials not yet available, and a minimum development period of 18 months. The recommendation was clear. Replication was impossible under existing circumstances. The German military's final situation report, dated May 7, 1945, declared, "American artillery employing proximity detonation has inflicted casualties exceeding all other weapon systems combined since December 1944. Countermeasures have proven ineffective. Immediate cessation of hostilities is recommended to preserve remaining forces from annihilation by superior technology." The proximity fuse program involved approximately 3% of all American physicists dedicated to a single weapon system. This concentration of scientific acumen, coupled with immense industrial capacity, yielded production figures that baffled German comprehension. Each production line at the Crosley Corporation was capable of assembling 500 units per hour. Workers executed individual assembly tasks in mere seconds with microscopic precision, repeating these actions thousands of times per shift. The manufacturing facilities operated around the clock, 7 days a week. On Christmas Day, 1944, production levels remained undiminished, even as German soldiers perished under proximity fuse bombardments in the Ardennes. American workers maintained peak output. The supply chain extended across the entire United States. Copper originated from Montana mines, silver from treasury reserves, and specialized plastics from chemical companies that had not existed 3 years prior. The industrial mobilization required was as intricate as the technology itself. In contrast, German ammunition production in 1945 relied heavily on forced labor, resulting in shells with only a 60% acceptable quality rate. Sabotage by these forced workers further reduced effective output. By March 1945, a mere 30% of German artillery shells functioned correctly. American VT fuses, despite their sophisticated electronics, achieved a remarkable 94% reliability. The narrative of the proximity fuse transcends mere technology and production statistics. It profoundly altered the combat experience for infantry on both sides. American soldiers gained a heightened sense of security, confident that their artillery could effectively neutralize entrenched enemy positions. German soldiers lost the psychological safety that earthworks and fortifications had provided for centuries. Accounts from veterans on both sides corroborate this transformation. American forward observers described calling in artillery fire missions with newfound assurance, knowing that proximity fuses would neutralize adversaries even within prepared defenses. German veterans recounted the feeling of helplessness upon hearing incoming artillery, realizing that seeking cover offered no effective protection. The medical ramifications were considerable. Casualties resulting from proximity fuse detonations presented unique challenges. The downward trajectory of fragments created wound patterns that military surgeons had not previously encountered. German medical services, already stretched thin, struggled to adapt to these novel casualty profiles. American medical personnel, conversely, benefited from the availability of penicillin and plasma, advantages unrelated to the proximity fuse but which amplified their effectiveness. The proximity fuse represented more than a tactical advantage. It exemplified a systemic superiority in integrating science, industry, and military application. While Germany pursued wonder weapons like the V-2 rockets, which consumed vast resources for minimal strategic effect, America mass-produced genuinely transformative technology and deployed it on a massive scale. The German V-2 program cost approximately $2 billion in equivalent resources and resulted in roughly 9,000 fatalities. The proximity fuse program cost half that amount and revolutionized both ground and anti-aircraft warfare. This comparison highlights divergent approaches to military technology. Germany emphasized groundbreaking platforms, while America focused on incremental improvements manufactured at scale. The proximity fuse also validated American organizational methodologies. The collaborative effort between Johns Hopkins scientists, industrial manufacturers, and military end users fostered a development cycle that transitioned from concept to mass production in under 3 years. Germany's fragmented research efforts and inter-service rivalries hindered comparable achievements. Following Germany's capitulation, American technical intelligence teams examined German proximity fuse research. They discovered sophisticated theoretical work, but no viable path to production. German scientists understood the underlying principles, but could not surmount manufacturing hurdles. Rheinmetall prototypes discovered in 1945, while technically sound, employed conventional vacuum tubes incapable of withstanding the extreme accelerations experienced during artillery firing. German engineers attempted various hardening techniques, but never achieved the reliability of American designs. Even if they had, Germany lacked the industrial capacity for mass production. Soviet forces received limited proximity fuse supplies through Lend-Lease, but no technical documentation. Soviet engineers spent 7 years reverse engineering captured samples before successfully producing their own proximity fuses in 1952. Even then, the quality remained inferior to American wartime production. This pattern of technological transfer underscores the complexity of proximity fuse manufacturing. Possessing mere examples was insufficient. Successful production demanded a robust industrial infrastructure, rigorous quality control systems, and manufacturing expertise that took years to cultivate. The story of the proximity fuse offers enduring lessons in military innovation. Firstly, incremental advancements to existing systems can prove more impactful than entirely novel weapons. Proximity fuses were still artillery shells, yet they revolutionized artillery effectiveness. Secondly, mass production capabilities are as crucial as technological sophistication. Germany developed jet aircraft, ballistic missiles, and advanced submarines, but could not produce them in decisive numbers. America manufactured millions of proximity fuses, each a sophisticated electronic device, and treated them as expendable ammunition. Thirdly, industrial integration is fundamental to military capability. The proximity fuse necessitated a coordinated effort involving scientists, engineers, manufacturers, and military users. American organizational culture facilitated this integration, whereas German institutional rivalries impeded it. Finally, secrecy, while offering operational advantages, also carries costs. Restricting the use of proximity fuses until December 1944 preserved tactical surprise but resulted in months of additional Allied casualties that might have been averted. The balance between security and operational advantage remains a persistent challenge in modern military technology. The proximity fuse raises profound ethical questions regarding technological warfare. It rendered killing more efficient, more certain, and more mathematically precise. German soldiers in their foxholes possessed no defense against projectiles detonating overhead at precisely calculated altitudes. This was not combat in any conventional sense. It was industrial-scale slaughter. Yet, proximity fuses also shortened the war. Every German division rendered ineffectual by proximity fused artillery represented one less division defending concentration camps. The technology that efficiently eliminated German soldiers simultaneously hastened the liberation of Nazi victims. Admiral Louis Strauss, who ranked proximity fuses among developments upon which victory very largely depended, understood this moral complexity. American veterans grappled with these implications. They were grateful for technology that saved American lives, but troubled by its devastating efficacy. Accounts describe discovering German positions where every soldier had perished simultaneously from the fragments of an airburst. This efficient killing removed human agency from the act of dying. Ultimately, the proximity fuse represented American strengths that extended beyond any single weapon. It demonstrated an industrial capacity capable of mass-producing sophistication, a scientific prowess to swiftly resolve complex challenges, and an organizational ability to coordinate development and production seamlessly. When German infantry encountered proximity-fused artillery in December 1944, they confronted more than a novel weapon. They faced the tangible manifestation of American industrial democracy. This was a system that could conceive, develop, manufacture, and deploy revolutionary technology while simultaneously engaged in a global conflict. The 30 feet separating shell detonation from ground impact symbolized the chasm between American capability and German assumptions. Within that brief span, measured by radio waves and timed by miniaturized electronics, lay the divergence between industrial democracy and totalitarian inefficiency. The proximity fuse transformed more than just World War II. It ushered in the era of smart weapons. Modern precision-guided munitions trace their lineage back to the miniaturized electronics first deployed in proximity fuses. The concept of embedding intelligence within ammunition, revolutionary in 1944, is now standard military practice. The manufacturing techniques refined for proximity fuses influenced post-war electronics production. The quality control standards, clean room procedures, and precision assembly methods became foundational for the semiconductor industry. The women who assembled proximity fuses in 1944 pioneered techniques still employed in electronics manufacturing today. The organizational lessons proved equally enduring. The integration of academic research, industrial production, and military application became the paradigm for Cold War weapons development. The proximity fuse program demonstrated that democratic societies could mobilize technology as effectively, perhaps even more so, than totalitarian regimes. This account is grounded in verified historical sources and documented evidence. Production figures are drawn from Bureau of Ordnance records. Technical specifications are derived from declassified Johns Hopkins Applied Physics Laboratory documents. Battle accounts are sourced from official after-action reports and military histories. Claims lacking substantiation have been omitted. No evidence supports specific casualty figures sometimes attributed to proximity fuses. German jamming attempts remain unsubstantiated. Some frequently repeated narratives appear to be composite accounts rather than documented events. What remains after careful verification is still extraordinary. The proximity fuse was genuinely revolutionary, transforming artillery from an area weapon into a precision system. Its development and mass production showcased American industrial supremacy. Its deployment hastened Allied victory. At an altitude of 30 feet, democracy triumphed over fascism, not solely through superior ideology, though America possessed a moral advantage, but through the mundane excellence of mass production. The proximity fuse, a miniaturized electronic device housed within an artillery shell, embodied everything Nazi Germany had miscalculated about American democracy. Where Germany perceived weakness in diversity, America discovered strength in mobilization. Jewish scientists who had fled Nazi persecution contributed to the development of the proximity fuse. Women who were barred from combat roles assembled the weapons that neutralized German soldiers. Democratic inefficiency somehow yielded 22 million sophisticated electronic devices, while totalitarian efficiency struggled to reliably manufacture basic ammunition. The German infantry who faced proximity fuses in December 1944 were arguably the world's finest soldiers. They had conquered much of Europe, fought on multiple fronts, and endured years of combat. They perished in their foxholes not from a lack of courage, but from encountering the future. They had 30 feet, the distance from airburst to impact, to recognize that their assumptions about American weakness were fundamentally flawed. In those fleeting moments, as fragments traveled from electronic detonation to human flesh, the delusions of the Third Reich collided with American reality. The proximity fuse annihilated more than just German soldiers. It destroyed the mythology of martial superiority, the romantic notion of defensive fortification, and the concept that courage alone could overcome technological advancement. In 30 feet of altitude, measured by miniature radios utilizing technology that should not have existed, Produced in quantities that should have been unattainable, America proclaimed that the future of warfare belonged to those capable of imagining, engineering, and mass-producing it. Every German soldier who died beneath a proximity fuse airburst perished as a consequence of American industrial philosophy made manifest, not in ideology, but in engineering, not in propaganda, but in production, not in theory, but in terminal ballistics. The shells that detonated 30 feet above German foxholes delivered democracy's argument against fascism in fragments, proving that free societies could outproduce, out-innovate, and ultimately outfight totalitarian powers. The proximity fuse was, in essence, democracy's perfect weapon, sophisticated yet mass-produced, complex yet reliable, expensive yet expendable. It inflicted casualties efficiently, not through malice, but through engineering excellence. It concluded battles not through barbarism, but through mathematics. It secured victory not through cruelty, but through industrial capability. The narrative of German infantry confronting proximity fuses is fundamentally a chronicle of the clash between past and future. Centuries-old traditional defensive tactics became obsolete in mere minutes. The very earth that had shielded soldiers since the dawn of warfare could no longer offer protection. The proximity fuse did not merely kill German soldiers. It rendered an entire paradigm of warfare defunct. In December 1944, German infantry had 30 feet before proximity fuse airbursts shredded their foxholes. Within that brief expanse lay the demarcation between the world that was and the world that would be. They measured their graves in meters. America measured victory in megahertz. The future had arrived, it was mass-produced, and it exploded at precisely 30 feet.